So first of all, thank you for all of you to be there and for the organization of this nice Congress. So for the next 10, 15 minutes, I will be summarizing some of the main results that I obtained in the framework of my PhD that I defended last year. So my PhD research focused on the cultural and behavioral aspect of the Middle Paleolithic inhabitants of the site of Nesher Ramla in Israel, which is dated to the MIS5. It was mostly based on the technological analysis of the lithic assemblage from this site. So this Middle Paleolithic site gains more attention thanks to the hominid fossil remains that were recently published, the so-called Middle Pleistocene Nesher Ramla Homo. It was published just last year. So the site of Nesher Ramla was discovered in 2010 in a limestone quarry and was excavated as a rescue program during about 12 months under the direction of Yossi Zeiner, which was already my PhD supervisor. So as a general chronocultural background, the central Levant during the Middle Paleolithic, which is dated between 250 and 45,000 years ago approximately, is a dynamic period due to paleoanthropological issues. Many problematics are raised due to the presence and possible interaction between different populations in that area. So as you can see on the map here, quite a number of sites are dated to the Middle Paleolithic period, some being attributed to Neanderthal, like the famous site of Amud or Kebara Cave, some to Homo sapiens, among them one of the oldest fossils of our species, which is the Homo sapiens from Mislia Cave. And a challenge has been added to this already complex picture is the identification of a new type of population known as the Nesher Ramla Homo. So this archaic Homo was discovered in the site of Nesher Ramla, which is situated here in central Levant in Israel between the modern city of Jerusalem and Tel Aviv. So this new type of population in the Levant is not a new species, as it was sometimes mentioned wrongly in the news, but is characterizing an archaic hominid from the Middle Pleistocene Paleodem, previously not identified in the Levant at the time, which is the MIS5. So the fossil remains that was found in this site are composed of a left parietal bone, that you see here, and an almost complete mandible with the remaining of a molar tooth. So what was surprising during the study of this fossil is that this bone presents distinctive combination of Neanderthal and archaic features. So the parietal bone bears features mostly observed in archaic Homo, falling into intermediate position between Neanderthal and Middle Pleistocene Homo clusters from African origin. The robust mandible present characteristic of archaic fossil from Europe, with some affinities with the Neanderthal, whereas the molar, this one, possess clear affinities with those found in Neanderthals in Europe. So all in all, what was very interesting, what is important to remember is that these fossils are unlikely affiliated to Homo sapiens. So I will not go into more details about this topic because it's beyond the field of my expertise, but if you're interested, I invited you to read the paper of Hershkovitz et al. 2021 about this fossil for more information. So this Nesher Ramla population have been using a specific type of site, which is not a cave and not a so-called open-air site, but an already formed circular depression, as you can see here, that have been created by the sagging and the deformation of the bedrock. So it's not a so-called open-air site because there is the wall of depression here that were protecting the occupant from the wind, and also the occupation area is then delimited by the wall. So as you can see here, there's the schematic representation of the depression. In the light brown or the archaeological deposit, and on the right photo is a photo during the excavation, as you can observe the thickness of the archaeological deposits. So the archaeological sequence measures about 8 meters. It was divided into 6 units. It was dated by OSL and ESR methods, and the cave falls into at the end of MIS6 and during the MIS5. There's new and more dates that will be published very soon, but all in all, they are all falling into this range of MIS5 and end of MIS6. So this site yielded a very large amount of faunal remains. as well as a huge assemblage of lithics that have been almost entirely studied so far. You can see here the amount of flint artifact that was found in the site, and the human remains I showed you before were just found in the bottom unit 6, just here. So today I will be summarizing 3 main behavioral patterns from which the results are mostly related to lithic technological study from unit 3 and 6. So I will discuss the most important technological behaviors, as well as the spatial and the use of space pattern. And finally, I will present shortly another aspect of the Nesher Ramla hominids trait, which is their possible symbolic behavior. So all these data are published, except the one for the spatial behavior, that in the spatial analysis, sorry, that I will be hopefully, it will be hopefully available in the next few months. So about the lithics, the centripetal Levallois reduction system is characterizing the main aspect of the technological behavior of the Nesher Ramla population. They produced and use in abundance the Levallois centripetal method for the production of rectangular and oval large Levallois flake like this as an example. All the reduction stage, of this method was observed at the site with the presence of large quantity of Levallois cores, both from preferential and recurrent mode of reduction, and also all the byproducts like the debordon flake and the pseudo Levallois flake and pseudo Levallois point were found in abundance also. To know that there is almost no point production in the site. But what's interesting is that the intense use of this method of reduction in the Levant and neighboring regions, such as the Arabian Peninsula, so we talk about the centripetal Levallois system, that we found only this reduction sequence in the Levant in the MAS5 and always associated with Homo sapiens, like in the set of Kabze or Skull, for example. And now we attest with our study that also the archaic population of Nesher Ramla produce and master this reduction sequence. So it implies that there is probably interaction and connection and also sharing of knowledge between these two populations that occur in the Levant. So this is the main reduction sequence that characterizes the site, but of course there is a minor reduction system like corn flake and other opportunistic reduction system, but it was in minority, sorry. Another important aspect of the technological behavior from this Nesher Ramla population is their use of a particular type of tool. So besides the production of the common scraper tool that you can find in most of the Middle Paleolithic sites in the Levant, they produce and use in a relatively high quantity a new type of tool previously unknown in that region, which consists in the production of a lateral tranché blow in one of two of the rotage edge of the tool. So this type of tool reach up to 50% of the retouch tool assemblage in some of the units. You can see here an example of a double scraper with one of the retouch edge modified by a lateral tranché blow here. This is also an example of this type of tool that was found in Nesher Ramla. So this is all this scraper-like tool modified by a lateral tranché blow here. So in the sites, in all the assemblage, we also found the spall, which are the result from the blow action. They also found in great quantity in the assemblage, but they were not used. They are just the waste of this production. So this type of tools is specific to the site of Nesher Ramla, and they were not found. They were found in all over the sequence at Nesher Ramla. So we argue that it most likely represents a cultural trait of this Nesher Ramla population. So the second aspect cultural aspect that I want to mention is the spatial and the use of space behavior. This preliminary result derived from the unit 3 at the site. This unit was chosen as a case study because it is a dense and relatively thin unit, showing minimal disturbances. This unit has yielded several combustion features. You can have a picture of one of the hearths here. and also many anthropogenic accumulation. As you can see, all these locus were found in the upper part of the unit 3. And all these observations were made during the excavation, and they already gave us a hint on the potential for the use of space analysis of the site. So then, to explore further on the use of space of the Nesher Ramla site, I combined different approach, mostly linked to the lithic remains, which involved the composition and the comparison of the lithic assemblage between different accumulation. I also processed to lithic refitting for the unit 3, and I produced some of density map of different type of lithic categories, together combined with a preliminary zooarchaeological result published by my colleague Frater Gerstein and colleagues from 2020. So here on the left is a schematic representation of Unit 3, with the drawings of the different artifact accumulation that were observed during the fieldwork. So the area of Unit 3 here, it's about like 40 or 45 square meters. It was artificially divided into 2 areas, the north here and the south area. Most of the refitting were found in this south area, the more dense, I mean, in terms of lithic industry, was found in this south area. As for example, we found like a very long sequence of refitting coming from this locus 33 here, and it was restricted in like about 1 square meters. So it possibly represents a single event of napping. Here are just 2 examples of the density map that I produced, one showing the repartition of the density of the cores, and the other one showing the density of the level of lakes. So even though lithic artifacts were found all over the occupation space, most of the density maps show clear accumulation and clear density, density area in this part of the site here, where there is accumulation and of combination features. So this aspect of space is still ongoing work, but thanks to the preliminary results based on the lithic and the archaeological data, an initial schema of the occupation of the site can be suggested. So we propose that the Nesher Ramla Homo organize their space according to different type of activity, with a central domestic activity, which is more probably a dropping zone, with mostly the flint napping and the animal processing next to the fireplaces. And in the north area is probably more related to specific activities area, like more specific butchering type of activities. So although we should keep in mind that this unit, even if it's a very thin unit of like 20 centimeters, it probably represents a palimpsest of several visits, even if it's like a short visit. So we suggest that the hominin might have kept the same space organization through time, at least during this occupation of Unit 3. So the last point that I want to mention is the possible symbolic behavior that the Nesher Ramla Homo may have engaged. So this proposition is based on the discovery of an inside bone, which is here. You can see it was found in a small accumulation, the locus 27. So this is a zoom on the bone when it was found during the excavation. So far it's the only engraved PC that was found on the site. And as you know, that this type of finding is quite rare during the Middle Paleolithic period. It consists in, it is an auroch, both primigenous shaft of a radius shaft. It bears 6 subparallel lines on one of the surface. To note that in this unit and in general in Nesher Ramla, the aurochs, the Bros primigenus, is the dominated species that was hunted at the site. So this is the other picture of the bones. So here the more or less parallel lines. They are quite long, like more than 4 centimeters and deep. So the butchery marks and other functional marks were excluded. Therefore, the incision represents a non-utilitarian production. The microscopic analysis demonstrates the presence of longitudinal striation inside the incision, like here in this microscopic photo. So this showed the intentionality and of creating such a mark on the bone. So the meaning of this production is unknown, but we hypothesize that the production of such an object with abstract pattern is not random and might bear some sort of symbolic purposes. So to conclude, the Nesher Ramla Homo occupied a specific setting in the landscape during the MIS5 in the Levant. Part of their lithic production organization is similar to what is known for contemporaneous Homo sapiens sites in the region, which implies close cultural interaction between the two populations. However, our study of the lithic have shown that this population also created and used a new type of tool, the tool with lateral tranché blow, which was not identified before in this region. Even though these modified tools could represent functional advantages, it probably also mostly represents a new cultural trait among this Levantine Middle Paleolithic population. Although the Nesher Ramla might not represent a habitation site, but rather a more specific task or shorter time duration, we suggest that this new type of population structure their space not in a random way, and they organize their space according to different types of activities. Finally, the discovery of a non-utilitarian object demonstrates that the archaic Homo Nesher Ramla developed abstract conception, possibly linked to a symbolic mediated behavior. So that's it. Thank you for your attention, and I would like to thank my PhD supervisor, Yossi Zeitner, and Professor Nama Görenbach. Thank you.
So hello everyone, and thank you for welcoming me to this conference. I'm going to take you to a time travel to the Mousterian with this presentation that is based on results obtained during one of my internships in the Laboratoire Géosciences Environnement Toulouse under the supervision of Claire Jaouet. So I am working with isotopes to study ancient diets, to understand ancient diets. And I'm sure some of you are already familiar with the methodology, but I'm going to describe it for those who don't know it. So traditionally, stable carbon and nitrogen stable isotopes were and are still analyzed in collagen fibers from fossil bones. And they give information about plants consumption, as we saw in the previous talk, but also marine food consumption and diet in general. However, collagen is the organic part of the bones, and it's very sensible to alteration through time and during the burial of the bones, of the fossils. So there is a time limit to the use of those elements. That's why another tissue can be studied. It's hydroxyapatite. It's the mineral part of bones and teeth. And elements and isotopic signature in this tissue can be preserved over a million years. That's why more and more studies are focusing on what we call non-traditional stable isotopes, and calcium, zinc, and strontium are part of those elements. So to understand the link between isotopes in bones and teeth and the diets, I need to talk about isotopic fractionation. It's when two or several isotopes from one element behave differently during a process, a chemical or physical process. And so the abundance of each isotopes will be different before and after the process. It means that the isotopic ratio, the isotopic signature will change during the process. If we focus on what happens in an ecosystem, we can take the example of an element X with two isotopes, A and B. And in an ecosystem, plants have a specific isotopic ratio. And when they are consumed by herbivores, when they are eaten, some processes can change this isotopic ratio during the metabolism. For example, one example is when bones and teeth are forming, one isotope can be preferentially incorporated into the hydroxyapatite compared to the other one. So the isotopic ratio in the bones of the herbivores will be different from the isotopic ratio of the plants that they are eating. And the same fractionation can happen between carnivores and herbivores. So the isotopic ratio in carnivores bone, in this example, will be lower than the isotopic ratio in herbivores bone. And we can follow this fractionation through the trophic chain using a notation, the delta notation, that is just comparing the isotopic signature of a sample to the one of an international standard. So in this example, when we get higher in the trophic chain, the delta of the bones and the teeth will decrease. Now, if we focus on zinc and strontium, several studies have already been made on modern materials to start to understand the systematic of these isotopic systems. For zinc, we studied delta 66 of zinc, and studies showed a decrease between herbivores and carnivore bones of this delta. For strontium, we are interested in the delta 88 strontium, and we see a decrease of this delta between plants and herbivores bones that consume those plants. So those two elements have a link with diet. So we want, the goal of this study was to apply those tools on fossil material, and especially to compare the results obtained with those two elements to see if they give complementary information or similar information. And also, what was interesting is that we can analyze those two elements and also calcium from one sampling. We don't have to sample for each element. So the fossil materials that I studied is from the Camille cave. It's a cave near Bordeaux in France. And the material is dated from the late Mousterian. There is no evidence of human occupation in this cave. Instead, it seems that it was a hyena den. So hyenas brought back their prey to eat them. So there is a lot of herbivores remains. Some herbivores that are extinct, like megaloceros, mammoth, woolly rhinos, and some that are still existing species. But also there is also carnivore remains, of course hyenas, but also a cave lion, and remains of animals that are considered to be omnivores, like the cave bear. We sampled both bones and teeth, and we took between 5 and 25 milligrams of sample. Then we needed to isolate zinc, strontium, and also calcium from the rest of the matrix and from each other. So we mashed up several column chemistry protocols to get all those elements from one single sampling. And then we used two different mass spectrometers to get the isotopic ratios. So now the results. I will present results obtained on enamel only because this tissue is more resistant than bone, and so it gives better results, but we obtain exactly the same conclusion for bone results. So let's start with zinc. The first thing we can see is that the delta 66 of zinc is, in average, lower in carnivore teeth than in herbivores teeth. But we see that for the hyenas, the values there is a broad range of values that is overlapping with herbivores. Another very interesting point is the isotopic signature of the cave bear that places it among the carnivores. And also the highest delta values are obtained for horses. Now considering strontium, we have the same results. The delta is lower in carnivore teeth than in herbivores. And we also have this broad range of value for hyenas. Among the herbivores, we can distinguish two different groups, one with very low value that are overlapping with carnivore value, constituted of both bison and megaloceros, and the other one with the rest of the herbivores that have very high values. So first, the first thing we can say is that the pattern observed in the fossils are similar to the one observed in modern materials for the living species. So it means that the biological isotopic signature is well preserved in enamel. To explain the broad range of values obtained for hyenas, we can consider the fact that they are not only eating meat, but also bone fragments when they are trying to reach bone marrow. So, and those two tissues have different isotopic signature. So it can explain why they have a broad range of isotopic values for hyenas. And an interesting point is the value of the cave bear that places him among carnivores, because the diet of this animal is still discussed, and some studies places him among pure herbivores and other among omnivores. So here we can say that this individual was at least omnivore, seems to be at least omnivore. And for the different delta strontium values obtained for herbivores, it's interesting because we explain them for now using metabolism with the difference between ruminant and non-ruminant herbivores, but we need to do more studies on modern materials to assess whether it's true or not. And to conclude, those results will be compared later with calcium results. And this multi-isotopic study will be interesting because those isotopic signature were also obtained on Neanderthals on other sites. And it's also a species for which the diet is discussed. So with all those results, we may be able to decipher a little bit more the diet of Neanderthal. So just a word about the pictures that I used in this presentation, and especially the beautiful drawings of Eric Lebrun. Yeah. So thank you for your attention. And if you have any question, I will be happy to answer it.
Well, thank you very much for the introduction, and I'm very happy to have the opportunity to present my work in this Congress. We have two Camille speakers working on Plio-Pleistocene carnivores, and I'm the second one. So I'm not going to talk about dogs, I'm going to talk about otters today, as Leah told you. Otters belong to carnivorans, which is a group of mammals that constitute one of the main predators in past and current ecosystems. And the earliest fossil record of carnivorans in Africa is in the early Miocene, is about 20 million years old. And since then, carnivorans have undergone several peaks of diversification and extinctions. And one of the peaks of extinctions in Africa occurred during the Plio-Pleistocene, where you have several large-bodied carnivorans, specifically hyenas and felids, that disappear from the fossil record. You have the extinctions of those large-bodied carnivores that could be linked to human evolution. So here you have a representation of the distribution of different genera of humans and carnivorans in Eastern Africa during the last 4 million years. And We have several proxies such as butchery marks on bones and stone tools and geochemistry analysis of tooth enamel, indicating that we have a shift in the diet of the human lineage during the Plio-Pleistocene with an amount of meat consumption that is more and more important. So humans became important predators of terrestrial ecosystems in Africa during the early Pleistocene, and along with carnivorans. And one of the hypotheses explaining the extension of large-bodied carnivorans is that during that time, humans and carnivorans were in competition for the same prey, potentially. So that would have conducted to the extinction of those large carnivorans. But this hypothesis is contested, and to test this and to understand the change of predatory guilds during that time period and the consequences of this change of guilds on the faunal community, we need to test this hypothesis at the basin level where trophic interactions operate. So that's what I'm doing in the Lower Omo Basin, in the Lower Omo Valley, sorry. I'm part of the Omo Group Research Expedition, including several paleontologists, archaeologists, geologists, working on different aspects, trying to understand past ecosystems of the Lower Omo Valley in southwestern Ethiopia. Indeed, there are continental outcrops along the river, the Omo River, that have delivered a rich fossil record in fluvial lacustrine sediments that are dated from about 3.6 to 1 million years ago. And these sediments occur in two formations, the Usno and the Shungura formation. And I'm going to talk about otters as large-bodied mammals. In fact, that doesn't seem necessarily it's not something that is common today, but in the fossil record, we have several occurrences of gigantism in otters. So we described a new species of the genus Enidriodon. Its name is Enidriodon homoensis. It is represented by dental and postcranial material coming from the Usno and Shungura formation in sites dated from 3.4 to 2.5 million years ago, approximately. So we have upper and lower carnassials that are very useful for carnivoran taxonomy. And we have also a femur. And dimensions of teeth and postcranial remains suggest that this otter might have weighed about 200 kilos. Enidriodon is a common fossil genus in Africa and in Asia. In Africa, you find this otter in late Miocene to early Pleistocene sites from 7 million years old to 1.9 million years old. And so most of those otters, you have 8 species, and 6 of those are in the eastern, in the Great Rift Valley in Eastern Africa. This species radiation could be linked to hydrographical changes related to climate change occurring during that time period in Africa. And the occurrence of Enidriodon in the Lower Omo Valley is one of the latest, one of the most recent before its extinction of the fossil record. The form from the Omo is closely related to Enidriodon dikicae, which is a species that we found in the Afar region in eastern Ethiopia, and also in the western Turkana Basin in the site of Kanapoy. Those two sites are older than the Omo occurrence in the Lower Omo Valley. There are many papers in the literature talking about the ecological niche of Enidriodon. There are many hypotheses about its ecology. First of all, my colleague Margaret Lewis in 2008 conducted a study on the femora of several species of Enidriodon in Africa. And she suggested that the proportions, at least, of the Omo femur would correspond to a terrestrial mammal very different from extant otters. In fact, the dimension, the length of the femur is particularly important for an aquatic mammal in general. And if you compare it to a sea otter, you can see pretty much the difference. The proximal epiphysis is very close in morphology, but the dimensions are different. So we investigated this aquaticity hypothesis of Enedriodon using oxygen-stable isotopes on tooth enamel. And we had 4 samples from the Shungura Formation. The oxygen values were way more positive compared to the HEPO values of 2 samples coming from the same sites in the Shungura Formation, which was quite surprising for an otter. And secondly, when we looked at the terrestrial carnivores, and in particular the felids and the hyenids, we can see the oxygen values encompassing by those mammals, and they show the same range of values that you can have also in Enedriodon. So both based on the postcranial remains and the oxygen stable isotopes results, we suggest that this otter might have been terrestrial. At least it might have swim way less than the extant otters, or in different ways. Now, looking at the diet, Enedriodon has a bunodont dentition, which means that the teeth are wide with low and conical cusps. And this is something that is present in many fossil otters. It's a convergent feature, but it's also present nowadays in the sea otter. It's very exacerbated, in fact, in the sea otter. And this bunodont dentition is often linked to adaptation to crush hard food items. So in the case of sea otters, I have a few videos, I hope they are working. There are 2 strategies. Either the sea otter is using a stone tool from the sea floor. It's putting the stone tool on its chest and then cracking the clam shell against the stone to crack open the shell and to eat the meats. Or it's using its teeth to open urchin shells and cracking also the shells of crabs typically. So its teeth are really useful here in the hard food items crushing. And we think that for the fossil of Enedriodon, it could have been something similar. In fact, many authors have suggested different types of prey depending on the fossil record associated with Enedriodon. They have suggested that this animal would have eaten catfish, crocodiles, turtles, and different kinds of mollusks. Here in the Shungura Formation, and especially in the member B of the type area, you can find a lot of remains of a giant freshwater oyster. It is a common oyster. This Etheria genus is a common oyster from the Miocene to the Pleistocene in the Turkana Basin system. And this oyster is still present nowadays in many African countries, and it is a very nutritive choice for food. It constitutes reefs along the margins of lakes in agitated waters. And we have hypothesized as the first hypothesis for food consumption that Enedriodon from the Homo would have fed on this oyster. So we looked at carbon stable isotopes of tooth enamel, and we found that the carbon values of Enedriodon were more positive compared to what was expected if this otter would have fed purely on Etheria, on the soft tissues of this giant oyster. Looking at terrestrial carnivores, we have pretty similar values to Enedriodon, especially in the median. And those felids that are studied here include both felids that were chasing in open areas and in more forested environments. For hyenids, they correspond to bone-cracking hyenas, so they might have fed on a diverse type of prey through carcasses. So Enedriodon and the terrestrial carnivores could have had a similar diet, preying on C3 plant eaters and C4 plant eaters, or on mixed feeders. So then if we look at the modern otters, we can find that the carbon isotope values are very negative compared to the extinct otter. Here you have 2 examples with the North American river otter and the Amazonian giant otter. Those otters prey on fish, frogs, and crayfish. So based on the postcranial remains and the oxygen and carbon isotope values, we suggest that this animal was mostly terrestrial and preying on terrestrial prey. The Bunodontus morphology could very well be related to scavenging behavior, as you can see nowadays in the wolverines and in hyenas. So as a conclusion, the ecological niches of Bunodont otters are not analogous to extant otters. So in that case, I'm talking just about Enidriodon. But of course, we need to increase our sample of teeth for isotope studies. So we need to sample more in Eastern Africa to look at the oxygen, carbon, and potentially also calcium to have an idea if this animal was a bone cracking otter potentially. Investigating also the diet using different proxies would be very important, using, for example, dental microwear texture analysis. And investigating the locomotor behavior of this otter by studying also other proxies like bone microstructure would be interesting. So we're going to continue this study on the fossil biodiversity and paleoecology of other carnivores from the Lower Omo Valley in order to trace the dynamics of the trophic interactions during the Plio-Pleistocene in Eastern Africa, and to test this hypothesis of extinctions of large-bodied mammals, large-bodied carnivores that are related to human evolution or related to environmental factors or both. So thank you very much for your attention. I was very happy to present. Thank you to all the organizers for this opportunity, and I take any question.